So here's the idea and the definition of a limit. This is not a purely mathematical definition with all the proper epsilons and little things that they'll give to you in calculus, but it's an idea definition that is a limit is something that you can get as close as you want to. So the other day when I was walking towards the wall, always cutting the distance I was away from the wall in half, I could get as close as I wanted to the wall. If someone said, no, you'll never get closer than 1 centimeter away, I'll say, well, when I'm 1 centimeter away, I'll walk half the distance and I will be closer. So I can get as close as I want to, and that's where the word arbitrarily means as close as I want to. So what it looks like in this first example, and this first example is really straightforward. It says, what happens to this expression, 3x minus 8, as you get really, really close to 5? And the way that we evaluate these is we just plug in 5. And say if I plug in exactly 5, can you see that I would get 3 times 5 is 15, minus 8, and that's 7. So if I got really close to 5, then I would get really, really close to 7. And the closer I got to 5, the closer my answer would get to 7. And so we would say that the limit as x approaches 5 of the 3x minus 8 is equal to 7. And that one's pretty straightforward. Where limits get interesting is when you get close to a number that you're not allowed to put in. And we saw that when we're dividing by 0 the other day. Another definition, continuous. We say a function is continuous if you could draw that graph. Again, this is a theoretical definition. If you could draw that graph through that point without having to lift your pencil. So for example, you can draw a parabola without having to lift your pencil. A parabola is continuous. There are some functions that might have a break, and then we would say at this place where I had to lift my pencil and go to another point, then that would be a point of discontinuity, and it wouldn't exist. You have drawn some graphs in the past. If we go back to grade 11, in grade 11 you had to graph this. No, that might have even been, yeah, grade 11, grade 10, maybe grade 12. You did this at some point. I think it might be grade 12. In grade 12 you did this. What you did, see if you remember, is you factored the top. And when you factored the top, you found out that it was x plus 4, x plus 2. Woo. And when it's divided by x plus 2, you went, hey, those cancel out, and I get just y equals x plus 4. Which is a line because it's y equals mx plus b. And you know that it has a y-intercept of 4 and a slope of 1, so up 1 over 1, up 1 over 1. And this would be the line. However, minus 2 is not allowed, because minus 2 in my original equation is a non-permissible value. X can't equal minus 2. So the way that you drew it, see if you remember this, at minus 2 you put a hole in your graph, and you labeled it as minus 2 comma, plug that in, 2. Now with that graph, we would have to lift our pen at minus 2 and then put our pencil and then put it down to draw it. So this graph isn't completely continuous. It has a point of discontinuity at x equals minus 2. For which kind of function? Tangent. Oh, yes. Tangent function also has a bunch of discontinuities because there's a bunch of asymptotes. So each of those places would be places where it's no longer continuous. Now, what we say is that limits exist always when graphs are continuous. If we looked at this graph and we said, what happens when x gets close to 0? This graph gets close to 4. We know that for sure. What happens when x gets close to 1? This graph gets close to 5. Limits are important at these points of discontinuity because we can also say what happens when x gets close to the non-permissible value of -2? It gets close to 2 because that's where we had a hole in our graph. Whoa, is that the next one on yours already? No, I'm missing some slides. I'll find them. So again, if you have something continuous that doesn't have any non-permissible values, it's just as easy as plugging that number in to find the limit. So for this one, x squared minus 1, as x gets close to 2, would be 3. You just plug in 2. 2 squared minus 1, it would equal 3. Okay? If you were showing your work for this one on a test and you wanted to show a lot of work, because I mean you could do that one in your head, but limit as x goes to 2 of x squared minus 1, as soon as you decide to plug in the value, you don't write limit anymore. Ooh, let's do lots of work. Let's draw out a number line here. 0, 1, 2, 4, go back 1, okay, 3. All right, good. Whew. But for that one, you could just write is equal to 3, because it's easy enough just to plug it in and do it in your head. But as soon as you go to plug in that value, you don't write the limit anymore. Any kind of algebra that you want to do before you plug it in, you'll always need to write limit as x goes to 2. Before that, and we'll see that in some examples coming up.